In this video, we are discussing the continuity of vector valued functions. We have already discussed limit of vector valued functions, and we know that the limit of a vector valued function is an expected value of the function or an expected constant vector which this function can approach. And as in the case of real valued functions, a vector valued function is said to be continuous at a given parameter if it can approach to the expected value of that function. That means if it has the expected value at the given point, then the function is continuous. Or more precisely, if the limit at a given point and the function's exact value at that point are same, then we say that the function is continuous at a given point. And this happens in the case of real valued functions and also in the case of vector valued functions. So, we can formally define the continuity of a vector valued function like this. A vector valued function, vector r, is continuous at a point A. A belongs to the corresponding parameter interval if limit t tends to A, vector r of t is equal to vector r of A. So, this is the expected value of the function at the point t is equal to A, and this is the actual value of the function at t is equal to A. And if these two are same, we say that the function is continuous at the point A, and a vector function r is said to be continuous on an interval I if it is continuous at every number in I. We already know how to find the limits of vector valued functions. The limits can be obtained by finding the limits of the component functions. So, a vector valued function is continuous at a point A if and only if each of its component functions is continuous at A. Now we can have some examples. Example 1. Find the intervals on which the vector function vector r is defined by r of t is equal to root t I plus 1 by t square minus 1 j plus ln tk is continuous. So here we have to find the intervals on which this given function is continuous. For that, we consider each of the component functions and find the intervals on which these functions can be continuous, and our final answer will be the intervals on which all these three functions can be continuous. So here we consider f of t is equal to root t, g of t is equal to 1 by t square minus 1, and h of t is equal to ln t. And f of t is continuous at all points when t greater than or equal to 0. When t square minus 1 not equal to 0, g of t is continuous. Therefore, g of t is continuous on all the points in the real line except t is equal to plus or minus 1. And ln t is continuous at all the points when t greater than 0. Now we are going to find the interval on which all these functions can be continuous, and therefore the required interval is open interval 0 to open 1 union 1 to infinity, open 1 to infinity. So in these intervals, that means on open interval 0, 1 and 1 to infinity, the valued function is continuous. Next, example 2. Find the intervals on which the vector function r of t is equal to r of t is equal to sin ti plus cos tj minus tan inverse tk is continuous. Here we know that the component functions sin t is continuous at all points of the real line. Cos t is also continuous on R, and tan inverse of t is also continuous on the same interval. So here vector r of t is defined at all points of the real line, or the parameter interval of vector r of t is minus infinity to infinity, and in this interval the function is continuous. Next we have another example. Find the intervals on which the function vector r of t is equal to e raised to minus ti plus cos root 4 minus t j plus t raised to 1 by 3k. Here f of t is equal to e raised to minus t, and it is defined for all t element of minus infinity to infinity. And now g of t is equal to cos square root of 4 minus t, and this function is defined when t less than or equal to 4, and it is continuous in that interval, in interval minus infinity to 4. And h of t is t raised to 1 by 3, and this function can be defined on all points of the real line. So the interval on which the given function is continuous is minus infinity to 4. Next example, r of t is equal to 2t divided by t square minus 4 vector I plus sin inverse t vector j plus 1 by t square minus 1 vector k. Here we consider f of t is equal to 2t by t square minus 4, and this function is continuous at all the points except t equal to plus or minus 2. So here t not equal to plus or minus 2. Now g of t is sin inverse t, and sin inverse t is defined on closed interval minus 1 1, and in that interval the function is continuous also. And h of t is 1 by t square minus 1. This function is also continuous at all the points except plus or minus 1. So parameter interval on which the given vector valued function is continuous is open interval minus 1 to 1. As we have already seen in these examples, we consider the intervals on which the component functions are continuous, and we take the interval on which all these functions can be continuous, and that happens when we take the intersection of all these intervals, and here the interval is minus 1 1. Thank you.